All right, so today we're going to start talking about probability. And so we're going to be in chapter 5. The good part about learning this virtually is that you can pause the video if you need to catch up or take a break, or if you just want to think about a problem. So we're going to look at some of the basic concepts of probability today. So first, let's define what probability is. So probability is going to be a proportion that compares the times an event occurs to the total number of possibilities. So we use this phrase in the long run a lot in probability, and it just means that we're going to assume that we're not just going to perform this experiment once. We're going to do it kind of over and over and over. So for instance, if we're going to do a coin toss, we're not just going to toss that coin one time. We're going to repeat that process a large number of times so that we can really kind of see what results we get over the long run. That's what that means. All right, so some terms that we're going to need to know. So the first one is going to be sample space, which I misspelled there. Tried to forget a word. So the sample space is going to contain all possible outcomes of a probability experiment. And when you list a set of choices, you usually list them in a curly brace. So let's take the coin toss that I just mentioned. So if we wanted to go list all the possibilities of results that you could get from a coin toss, notice there's only two choices, right? So we would use a curly brace and we would say one of the choices it could land on if we did a coin toss is heads, and the other chance or the other choice is tails. Okay, and so you always just list them separated by commas and then surrounded by the curly brace. So that's what a sample space is. An event, we're going to refer to all these words in the probability sections in this class. An event is an outcome or sometimes collection of outcomes if we're looking for more than one thing to occur from a sample space. So in our coin toss example, heads would be one event and tails would be another event. A probability model basically is usually just a listing that consists of everything in the sample space. So a list of all the possibilities of outcomes basically, and then the probability of each event. Okay, some books call this a probability distribution, but this book calls it a probability model most of the time. So here's some notation that we're going to kind of use going forward. We're going to use a capital P to stand for probability, and then whatever event we're trying to track, we put that in parentheses. So the P of A here means the probability of event A happening. Okay. And the formula for probability of A is sometimes pretty simple. And so in its basic form, it's just the number of outcomes of the event A. So in other words, you count how many occurrences there are of what you want to happen, and you put that over the total number of outcomes in the sample space. So it's simply just a fraction. That of course can be changed to a decimal. I usually word it just a little bit differently, but the probability of A is basically the number of desired outcomes over the total number of outcomes. In other words, how many of what you want to happen are there, that goes on top, and then how many total options are there, and that goes on bottom. Okay, so the probability of A, if it's in decimal form, and it will be a lot in this unit, it should be a decimal between 0 and 1. Which corresponds to percentages between 0 and 100. So remember, when you change a decimal to a percentage to a decimal, you move the decimal place twice. So a probability of 0 means the event cannot happen. And 1 means it's sure to happen. But often our probabilities will be somewhere in between 0 and 1. Okay, the closer it is to 0, the less likely it is to occur. The closer it is to 1, the more likely it is to occur. Okay. All right, so let's go ahead and look at a couple examples. So let's say that a family has 3 children. And I'm going to ask you to find the probabilities of some events. So find the probability that, let's see if I can slide another page here. So the first one I want you to find is the probability that there are exactly 2 girls. Okay, exactly 2 is different than just saying 2, because 2 could mean 2 or more. Okay, so exactly 2 means just what it sounds like, just 2. And then the second thing is I want you to find the probability that all 3 children have the same gender. Okay. So what we're going to do first, and you can do this for smaller sets, is first we're going to list the possible outcomes, and this will be a good practice of listing a sample space. And then from that we should be able to come up with our ratios or our probabilities. The biggest concern with sample space is you have to make sure that you list them all. Okay, so we're going to use our curly brace. So go in some sort of order. So they could all 3 be boys. B is going to stand for boy and G is going to stand for girl. Okay. The first 2 could be boys followed by a girl. It could be boy, girl, girl. I'm doing all the ones where there's a boy first and then kind of going from there. And then it also could be boy, girl, boy. I think that's all the possibilities where a boy is the oldest. Okay, so this is literally the progression of the 3 kids. So boy, 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 girl, boy, girl, girl. Okay, but now we have the same things going on for if the girl is first. So we've got girl, 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 boy, girl, boy, girl. And I didn't necessarily go in really any systematic order here. I kind of switched that up, but that's okay. Okay. But notice that's the only 8 possibilities, and you could think about that for a minute and you would notice that that's true. So now that we have 8 possibilities, we can find the probability pretty easily. So the probability of exactly 2 girls okay, is going to be a ratio, something over something else. So first you need to go back up to your list and count the number of times exactly two girls came up. So here's one, right? Here's another. And trying to see if I repeated something. Just give me a minute, I'm looking. Okay, no, I think there's only two, so I was just looking at my answer, which wasn't quite right. So there's one right here, right? And then there's one right here, so I think there's only two possibilities out of 8 total. Okay, so notice if we were going to label it, this is the number of outcomes with 2 girls. And then this is the total number of outcomes. Oh, okay. So I figured out where I missed it. So I missed one right there, which y'all at home are probably like, yeah, no duh. So notice there's actually 1 here, 2 here, and 3 here. I thought it was 3, but just for some reason I was overlooking that one in my list. That kind of demonstrates a point that I made, though. It's easy to forget them, and then sometimes it's easier to just space out, and when you're looking at them, it doesn't look like it should. So just kind of just what happened to me. So it should be 3 out of 8. Sorry about that. Okay, but then we can change that to a decimal. You just use your calculator to divide, and you end up getting 0.375. Notice that's a decimal between 0 and 1. But this stands for 37.5%. So I'm going to circle all of these. You're going to need to know how to change these from fraction form to decimal form to percentage form. Really, all 3 of them need to be something that you can do. All right, so now let's find the probability of all 3 being the same gender. This time maybe I'll count it right. So again, we want something over something else, and the bottom's kind of already been decided, right? This is still the total number of outcomes. And so now we just need to go up to our sample space and count any time where there were all 3 the same gender. So it looks like that's 1, and it looks like that's 1, right? So 2. Okay. So this is the number of outcomes with all girls or all boys. Okay. When you give the answer in fraction form, try to reduce it. Notice 3/8 didn't reduce, but this one does reduce to 1/4, so we'll go ahead and do that, which is 0.25 or 25%. Okay. So sometimes probability can be found just that simply. You just have to list out all the possibilities and then come up with your ratio. All right, so let's look at another one. So let's say that we surveyed 600 likely voters in a city. And 420 of those say they plan to vote for the current constable to be reelected. So we're going to take this 600 voter data and we're going to try to find the probability that maybe the next person we survey, that a random surveyed voter plans to vote for the constable. You know, and this brings up a good point about probability. We are often looking at past events to try to predict future events. That's actually usually the point of probability. So we've already collected data on 420 actually have 600 people, 420 of whom say they're going to vote for the constable, and so we're trying to use that to find the probability that just a random voter that we pick is going to vote for that constable. So the probability of the surveyed voter planning to vote for the constable. So notice this time the event description is kind of long, but we're using our P of whatever notation. Okay, and so the probability is the number of cases that said they voted for him over the total number that were surveyed. And so this comes out to be 7/10 or 0.7 or 70%. Kind of a small thing, but make sure that when you change your, it's not really a small thing, when you change your decimals to a percentage, 0.7 is actually 70%, whereas 0.07 would be 7%. So make sure that you move that decimal place twice. Okay. And by the way, back to this example right here. In chapter 1, we talked about how to come up with a good sample. And so you would want to, if you were going to try to predict future voters based on this survey of 600 voters, then you would need to have made sure that you picked a good sampling method. Okay, remember how we talked about some of them were better than others? So you'd want to make sure that the sampling or the sample that you choose is representative of the whole group. Okay. All right, so we're going to talk a lot about this term this semester. Okay. And that is an unusual event. I think we all kind of know what that means, maybe by definition, but there's actually a specific definition in stats for that. So it's an event whose probability is small, and usually small is defined as anything less than 5%. Not always, but our standard is going to be 5% or, less than 5%. There might be some instances, though, where you would want to be more or less specific than that. But often anything with a probability of less than 0.05 is considered unusual. But that standard can change. So just know that that's kind of a moving target. Okay, so practically speaking, some of the most probably misunderstood concepts of probability is the difference between the two types of probability. Okay, one is theoretical probability. Okay, and theoretical probability is what should happen in theory. Okay, and so an example of that is, this is just perfect theory. So if I toss a coin, let's just take a coin toss for instance. If I toss a coin 100 times, if the world is perfect, think about what that should mean, right? I should get 50 heads and 50 tails. Okay, because there's a 50% chance of either one, right? So again, that's like perfect world scenario. That's what should happen. Okay, but often what does happen is a bit different than what should happen. So we also have empirical or experimental probability. I think this book calls it empirical, but a lot of textbooks call it experimental. And that is just what does happen based on actual results. Sometimes what does happen is what, quote, should happen, but sometimes it varies a little bit from what we expect. Okay, so let's take that coin toss again. So let's say I toss a coin 100 times and I actually record my results. But but let's say that I get 46 heads and 54 tails. Okay. Notice that's not crazy different from what we expected, which was 50 and 50. Okay, but it is a little bit different. Okay. It is people's misunderstanding of this that drives the whole gambling industry as a whole. Okay. So if you go by what should happen in every gambling game out there, okay, so this is just a public service announcement, in every gambling game out there you should lose because the casino or the house has structured the game so that they always have the advantage. Okay, but what we're betting on when we go and play is that we're hoping that the experimental probability will be different than the theoretical probability. Okay, that's what we're hoping for. Sometimes it happens, but if you look at the large numbers, which is what we're looking at next, if you look at people as a whole, the reason the casinos are making so much money is because as a whole people are losing because they're structured. The games are structured so that the house always has the advantage. So the law of large numbers just says the more times you repeat a probability experiment, the closer the empirical probability will come to the theoretical. The theoretical doesn't change. The theoretical is the theory. It is what it is. But the empirical or experimental will kind of conform to that theoretical the more often you do the experiment. So let's go back to our coin toss example. If I only toss the coin twice, that wouldn't be large numbers of times, right? So if I toss the coin twice, and let's just say I got heads both times, it would be a mistake for me to say, oh, I'm always going to get heads because I flipped the coin twice and I got heads, right? When it would be better if I actually completed the experiment more often. So if you went up to maybe, say, 1,000 times, you would expect this 56 and 54 to be closer to 50-50. Okay, of course it would be bigger numbers because it's 1,000 times, but I'm just saying the percentages should be closer and closer to what we expect the more often we do it. So, back to the gambling example, you might win one time, but if you go to the casino every day, if you go to the casino every week, or if you just take all of their customers together and kind of lump them together, the house is going to have the advantage because over the long haul, when you take large numbers into account, the experimental probability is going to much more closely resemble the theoretical probability. All right, so let's look at a word problem where we take a really large quantity of data that would definitely qualify for the law of large numbers and see what we get. So according to the census data for a certain year, there were 2,046,935 boys born and 1,952,451 girls born in the U.S. So this kind of goes without saying, but the theoretical probability, without science intervention, I guess I should say, of any child being born a boy is what? If I say the theoretical probability, well, the theoretical probability is unchanging, right? It's 1 out of 2. There's boy and a girl, you got 2 shots, right? Two possibilities, and only one of them is what we're asking about in this case, which is a boy. Okay, but I want you to find the empirical probability of a random child in this year being born a boy. In other words, maybe the census has a list of all the children born, and you're just going to close your eyes and point at one of them, and you're going to open your eyes and see, was that a boy or was that a girl? So the point is, empirical means the same thing as experimental. And so first we're going to need to have a total. Okay, so we're going to need to figure out what the total is. And for that, we're going to take the number of boys plus the number of girls. So we're going to use our calculator, but we get 3,999,386. I'll let you check me on that, but I'm pretty sure that's right. And so the experimental probability of a boy, again, if we asked for theoretical, it would always be 1 out of 2. Okay? But the empirical or experimental probability would be the number of boys, which was the 2,046,935 number, over the total number of babies that year, which was 3,999,386. Okay. And so what you end up getting is, if we round it to 4 decimal places, let's round it to 4 decimal places, because that means when we change it to a percentage, we still have 2 decimal places. Okay. So notice it's not exactly 50%, but notice that it's close. Okay, because we took a large number of babies into account, it's pretty close to what we expected. Okay. So just make sure that you really understand how to find probability, and essentially make sure that you understand how to tell the difference between theoretical and empirical probability. You know, and even if your family or you are not a gambler, again, there's all kinds, I'm going to go back up here and I'll slide it back down in a minute, but there's all kinds of people that don't understand the difference between these two. Okay, if you've ever heard someone who are having kids say, you know, we've had 4 boys, so we're going to try again because we're bound to get a girl the next time. And the problem with that logic is that theoretically, your chances of having a girl or a boy with any baby is 1 out of 2, right? It doesn't really matter what the previous 4 babies were, right? Genetics and the DNA that are being supplied by the parents don't care that there were, you know, 4 boys, right? It doesn't matter. The next baby would still have a 50-50 chance of being a girl or a boy. So a lot of people just intuitively don't understand the difference between these two. So make sure that you understand. So in theory, theory is unchanging, but in practice, sometimes it doesn't always come out with the probabilities we're expecting in theoretical probability.